Today we have Peggy from our QA team. She's going to be talking about techniques to study external flow, but really many of the tips and tricks and workflows she's going to cover can really be applied to just about anything. So that may have been a little bit of a misnomer. And as normal procedure, we're going to start off with just some polls to help Peggy know who's all out there and what their experiences are. First off, this talk is actually going to be based around sailing a little bit. It's a big love of Peggy's, and she just wants to know, have you ever gone sailing before? And right now, it's about 40% yes, 60% no. Decent split. I'd put myself in the yes column. I like to sail as well. So we'll close that. And just so you can see the results, about 43% yes. And we'll go right into the next one now. As you may have been aware, I actually led a turbulence model webinar a few weeks ago. Just want to know how you may have watched that, attended live, watched later on YouTube, or maybe had no idea that it existed and will look to watch it soon on YouTube. People were voting quickly, which I appreciate. And I'll close that. And just share the response so you can see, what everybody responded. Mostly no, and that's fine. You don't really need to know a whole lot about it for this webinar. It'll just be referenced during one slide towards the end. Okay, Peggy, if you go to the next slide for me. Okay, so for the 56% that said they had not seen it and will look to watch it soon, hopefully, that is actually located within YouTube. If you look for the Autodesk Sim 360 channel, and there's a playlist there, we renamed it, Build Your Simulation IQ, you'll be able to go back to, that was actually our 5th webinar, and I think it's a great start for kind of a 3-part series where we talked about turbulence. Now we're talking about just general modeling and some tips and tricks, and then next month we'll be looking to talk about benchmarking flow over an airfoil, specifically NACA 0012. For those that maybe this is their first time joining, maybe you got a direct email or you found it online, in the future, the best place to see the announcements are within any one of the simulation forums, and for this one, I'd probably think you join the CFD forum. But if you're social inclined, then maybe Twitter, Facebook, and LinkedIn, you can track some of those different feeds. Next slide, Peggy. And in terms of in the news, I talked about Project Arrow and Dalton during our last webinar, and this newer project that came out, which will be talked about a little bit by Peggy, is Project Ventus, which I'm just naming Next Generation Mesher. And at this point, I'll hand this over to Peggy so she can take it away.
Thanks, Royce. So I'm Peggy Menzies. I've been working with CFD for about 20 years. And to me, it was my love of sailing that probably really sparked my interest in fluid flow analysis to begin with. And to me, nothing speaks more of external flow as the America's Cup. And no, I'm not talking about flow over the cup itself, but these racing machines. They're taking the energy from the environment and transforming it into just colossal speed and excitement and everything else. And to me, these are great examples of how we can pursue studying for external flow. But some of the techniques we're going to learn, as we said, it's applicable to just about any simulation you use. So these boats, they're meant for speed. There's enormous amounts of money poured into the design of the sails, the hulls, every aspect of these boats so that they can get the most speed they can. And sometimes they go really fast, and well, sometimes they really crash. But thinking more in terms of maybe what we would think of as a more traditional sailboat, this is an older style America's Cup boat. And one of the things that I always found fascinating in talking to sail makers, sail designers, is you see these stripes on the sails and you think, oh, they're just, logos, things of that sort to try and just make the boats look really sporty. And no, they're not. The sail designers actually have cameras on the deck of the boat pointed up at the sails, and they use those lines for some of the optics to help identify the sail's shape. And that feedback gets back to the crew to say, this shape is what I designed for these conditions, or no, it's not, and you need to adjust, so that they can get every bit of power and speed out of the sails as possible. So we're talking that level of sophisticated design to make these big racing boats. So any model that you're going to simulate or you want to do this design, it's going to start with a CAD model. And so this is the model I played with to prepare for this presentation. It's a great model from the standpoint of what tips and tricks and techniques I used to get the simulation. So we're going to go over some of those techniques to make sure you can use them in whatever you're trying to analyze. So I got this model from GrabCAD. It was a beautiful model, and somebody did some great artwork with some of the renderings. So to take something like this and say, wow, I really want to design sails, or I want to improve my design, there's these pieces of the puzzle that we need to put together to build our simulation, to make sure we're asking from the computer the right questions, because then we'll get the right answers. So to me, it kind of evolves into 3 steps. So we have kind of this CAD preparation, where actually most of the work is the thinking work, where you're going to evaluate the physics. And then we figure out whether we want to defeature, or we could try the labs project that'll go into. Another step, or another piece of the puzzle to trying to come up with an accurate simulation, is to achieve mesh quality. So I'm going to go over some out-of-the-box techniques that might be useful, again, for external or any other kind of simulation you might be working on. I'm going to review about our surface autosizing and edge refinement techniques. These are some techniques that you can leverage to achieve some really nice meshes. And one thing that's kind of a little bit particular to external flow, but internal flow with large cavities has the same problem. How do you propagate the mesh into the flow domain? So we'll cover that when we go over the mesh quality. Last, we're going to go over some of the better settings that you would use, some of the solver settings, and this is that turbulence modeling that was alluded to from an earlier presentation. We're going to use the advanced method. And something new in our 2015 product, or our release, was about spatial variation. These are boundary conditions that will allow you to set a gradient for what you're doing. Really important for external flow, but useful for anything else as well. So let's take it away. Talking about CAD prep. And really what I said was the first part of any kind of simulation is really the thinking part. Evaluate the physics. What's significant for that simulation? Now I'm not talking about, oh, let's figure out what the Navier-Stokes equations are. Well, that's what the tool's going to do for us. But what are we really trying to achieve? So what leads to the best design? So I'm going to emphasize this on our example as the sailboat. What's going to make the best design? Probably one that goes the fastest, right? Might work for a car or race car or something like that too. So when you think about a sailboat, you can think about the sails. Well, what aspect of the sails? We have the shape, the actual airfoil shape that the sails were designed with, the trim, how relative to the position of the boat, or even how the sails interact with each other, just to name a few. So this would be airflow in our analysis. But we can also look at the hull. You've got the shape of the hull that changes all the maneuverability of the sailboat. The length of the hull that might affect the overall speed because of the bow length. Or the keel that without, your boat's not going to go where you want it to. So any of those design parameters could matter too. Well, now we're talking about water over the hull, different physics. Or we could even get into how the crew moves across the deck. What kind of layout? Does the crew stumble across each other as they're trying to manage the sails? If the skipper can't see where he's going because there's a blockage problem, you're not going to win the race. So there's many different ways to get the best design of your sailboat. And for my example, we're going to focus on the sails. So when I'm talking about, let's evaluate the physics, if we're talking about the sails and we're working on the shape of the sails, we've isolated the physics now. We're going to do air over the sails. And it's very important to have thought about this ahead of time because we want our CAD to model to help us achieve just that. So we've isolated the physics to the airflow over the sails. Now we want to maybe think about what kind of test cases we're looking at. Since I'm dealing with the shape of the sails or the sail interaction perhaps, my test cases might be, well, my model's close hauled. The sails are pulled in pretty tight, so maybe the boat can sail at about 25 degrees relative to the wind. Well, so maybe my test case is going to be the sailboat at 25 degrees to the relative wind, and I need to evaluate it at 24 degrees or maybe 26 degrees. I want my sailboat to pinch up and cut off the competition. How much speed am I going to lose when I go closer to the wind? Or if I want a foot off or be at a broader angle to the wind, maybe I can improve my speed so much that I'm going to dust the competition. So those would be important design criteria for the sailboat. When I establish my test cases, then I also need to think about the environment. Now this is kind of particular to external flows. For the environment, we're going to model the air. We're putting the boat in a box of air so that we can simulate the environment. We're modeling the air. It's kind of reverse thinking, you know, it's like, oh, I'm building a sailboat. Why would I care about the air? Well, that's what's flowing. So the size matters. And in this picture, let's see if I can get it to show up. All right, imagine yourself putting this box around the object that you want to study. So this box is around my sailboat. When I do that, I need to make an air volume that's 2 times in length going upwind. I need it to go 3 times in the length behind it, and that's because of the wake. We'll talk about that. We can go 2 times as wide as the box on either side. It's ideal if you can keep it symmetric, if your flow is expected to be symmetric. And you need to go at least 3 times as high for your complete flow volume. Now, all these numbers are in our help documentation, so you don't need to memorize it. It's an easy matter to find. But this idea of 3 times the length in behind, that starts making a pretty hefty size of the box. Now, why do we need this? It's because the wake matters. If anybody's been on an airplane trying to land at one of our bigger airports or something like that, you might have to do an extra loop around the airport, flying around, while you wait for the wake turbulence to clear. That wake turbulence is from the plane that landed in front of your plane, and that wake is real. It's not a simulation artifact. It is very real, and a plane that has landed can leave a wake that is still settled over the airport that can affect the plane that you're in, and that's why airports have to have such timing to space out the plane so that the wake can dissipate. So when we're trying to do the simulation, if we really haven't captured the wake, we really haven't captured what's going on with the flow, and our answer won't be as accurate. So that's why we ask the box to be a little bit longer to capture that wake. So all of this is the thinking part before we even are looking at our CAD. Now, from our CAD model, this is my original model as I grabbed it from GrabCAD, and it's a very rich, detailed model. It was just a beautiful model. Credit to who made it. In it, there's this traveler, just as an example, there's this traveler block arrangement in the cockpit, and also each one of the winches, very detailed and very rich in modeling. This knob alone is made of 3 parts. Now, if I'm studying the sails on the sailboat, do I really need this detail? Now, if I were doing a deck layout, oh, I would most certainly need this layout. But because I'm just going to study the sails and the flow over the sails, I go into my CAD and I change the visibility of these parts. I just make them invisible. And so when I launch from my CAD, this is what I see. It's a very clean hull. I'm not going to waste any of my elements down in this area, and I have the sails exactly as I would like them so that I can do quite a study of what's going on with the flow across those sails. Now, if that's too much effort, we do have Project Ventus for Simulation CFD. It's available in labs now. Love for you all to try it. I took the model exactly as I got it from GrabCAD, chucked it right into Project Ventus with a little bit of adjustments on the mesh settings. I got this beautiful mesh. You can see all the rich detail that was provided in the model, some of the winches, all the deck fittings and whatnot. I didn't have to fuss with my CAD to get this. But with a little bit of effort, I have a very, very smooth mesh across all my sails, and this is perfectly suitable then to bring into CFD, and away we go with our analysis. So since we're talking about mesh, let's go on to the next piece of the puzzle. We're talking about the mesh quality. So here are some out-of-the-box techniques that you might try for any of your analysis that are going on. In particular to this analysis, we're talking about sales, but really I'm talking about materials. Wait a minute, I'm talking about mesh. No, I'm talking about materials. We can use our choice of materials to greatly simplify the mesh. If you're working on some kind of analysis that has a very detailed filter, well, we have a material device that will mimic that filter without having to have any of the details of the filter. You can learn an awful lot about your analysis by using those simplifying material devices for this.
Yep, I can still hear you. Sound great. One question did come in, Peggy, while I have you on the right now. The mesh that you just showed, do you have any idea how many elements that had?
I'm sorry, I didn't record that.
Okay.
It will mesh a little bit more intensely than it will with all that detail. And so that's why you might want to consider the defeature option. But by giving you the labs option, you have a choice, and you choose which option is best for you. So as far as the out-of-the-box and selecting materials, when we think about the sails in an analysis, we're talking a 12-meter yacht. How thick are those sails? Really, they're obnoxiously thin volumes, very shapely, that are hard to mesh. Well, what can we do with those films? We can make them a surface part. Make the sail by selecting the surface and applying some kind of solid material to it, and this greatly simplifies how the mesh looks. So you can see over here on the right, my pointer to work, this actually becomes the sail itself, and we're able to get a very nice, smooth transition with our mesh layers to mimic where the sail is, because the sail, all we needed to do is deflect the flow. Change the direction of the flow that takes the energy from the environment and pours it into the boat. And that's what we're trying to achieve. So by using surface parts, we can greatly simplify how we would mesh this model. Think about your materials when you're talking about mesh for any of your analyses. Some of our material devices are there to help. All right. Now, I absolutely contrived this model to exaggerate what I've seen in the past. When you have very thin volumes, the mesher can sometimes start to clump, or what I call these blotches. And so I'm trying to, highlight what these blotches look like, where out of nowhere you see a clustering of nodes. Like I said, I actually worked very hard to contrive this in this model. But these ultra-thin volumes of organic shapes, anything shapely, you can see maybe some mesh anomalies, and you're going to have a less accurate solution. So the blotches are bad for flow. If you see that, you probably want to correct it. Here's a technique to do that. With the model in CFD, I used surface auto-sizing. I leveraged our edge refinement technique too, and it worked very well for this model. What this means is when you're on the mesh panel and you click Edit, there's the Advanced button. Using that Advanced button, I changed my surface refinement, specifically the growth rate. By default, it's set to about 1.2. I tuned it down just a little bit to 1.1. What this allowed me to do is that these areas that were very finely meshed will grow as they propagate to areas that are larger sections of the surface. By turning that down, it had a smoother transition to these larger areas. Okay, in addition to this, you'll notice at some of the corners to the sails, at the clew and the foot, there was a lot of detail in the model. So it created very fine mesh in this area. Along the rest of the leech, there was nothing in the geometry to drive keeping a fineness here, yet I know the flow is going to be separating at this point because it's the end, the trailing edge of the sail. So I used edge refinement by selecting to use surface refinement and refine, and then I selected the edges and added some edge refinement as well. Last, one of the things peculiar about meshing for external flow volumes is we got to treat that wake. I just told you about how important that wake is. So we have mesh refinement regions. Whenever you need, for whatever kind of analysis, you need more mesh in a specific area of your model, particularly when there's no geometry to help guide the mesh, you can always use these mesh refinement regions to try and capture a wake or a jetting fluid or an area where there's a lot of circulation, perhaps, in your flow. So in this case, my model is actually oriented this way. I apply the wind direction at an angle, so I actually put in my external or my mesh refinement region, and this is the feature in CFD, not in CAD, and I angled it to kind of match how I'd like the wake to go. So you can see its effect in the mesh, quite a bit of fineness here. I allowed it to scale and auto size, but I didn't force really fine mesh in the outer area. By doing this, I'm conserving my mesh, I'm conserving my computational resources, and I'm able to still capture the accuracy I'm going to need. All right, so the bottom line is you need to mesh like you mean it if you want very accurate results. One aspect is that you can use diagnostics to check your model. You will check this MRL. This is the minimum refinement length. The idea is if when you go to check your MRL, your model lights up with red arrows, you probably need to scale that down a little bit. It's saying that anything that's lighting up with a red arrow is smaller than how the mesh is going to try and treat it. So by scaling that down a little bit, you'll get a finer mesh on the areas that are more intricate in your model. Leverage regions whenever you need to, especially to treat the wake or any other areas where the flow's doing something that you need to capture. For enhancement, I'm going to recommend extra layers. Now that's because we're going to talk about a turbulence model that needs these extra layers. For external flow, I would recommend that you add these extra layers. And last, on that enhancement page, I'm going to recommend that you add a blending flag. This is very particular to external flow or any other flow where the flow is going around convex corners. As anybody knows from flow, going around a convex corner, you're going to have the Bernoulli effect, Coanda effect. Your flow is going to try and either stick to the corner or it's going to separate, and you need that extra mesh to help the solver figure out what it should be doing. So with that flag, we insert extra boundary layer elements in that convex corner so that it's distorted. Now, something else you can do, we try to make this very easy for you. We have mesh adaptation. If you can, you let out mesh adaptation do all this for you. And one thing you would do is you would go ahead and turn mesh, enable adaptation. For external flows, I would definitely say allow coarsening. This will keep you from overmeshing some of the outer regions of your flow domain and keep you computationally efficient. Flow angularity would be on by default, but I recommend you add your free shear layers and also to check on for external flow. Yes?
I don't know if it's on both of our ends, but on my end, my audio keeps cutting out, and I get a little warning that I lost connection. I think it's a GoToWebinar issue, so if you could just step back, not a whole lot. It was right after when you stopped talking about the blending flag. Sorry about that.
Okay, so review the blending flag?
Nope, just after the blending flag.
Okay, so what I was saying is that we were trying very hard to make it easy for you in CFD to mesh like you mean it. So you can just turn on mesh adaptation. It's a feature we have for you that allows you to, with a couple of clicks, have the mesher figure out where your flow needs more mesh, and it'll put it in for you. All right, so one of the ways to do this is you would go ahead and enable the adaptation with the checkbox. I recommend, for at least for external flow, to allow coarsening. By allowing coarsening, it's keeping you computationally efficient. You're not going to put an awful lot of mesh in areas where there's nothing interesting going on with the flow. Flow angularity is on by default, but I recommend free shear layers and also turning on external flow. This will really help the mesher understand what's going on with your model, why there's areas where the flow is just kind of proceeding straight along, and why there's areas with the wake, and there might be some shear going on. The transient features is also recommended to turn on. This does make it multiply the number of cycles that you run, but for an external analysis, the wake really is transient, but we're going to solve it steady state. We do this for computational efficiency, meaning it'll run faster and you'll get better performance. But to help understand that, we kind of mask these transient features to be kind of sort of quasi-steady state, and that's why you would want to turn this on. I would also recommend Y+ adaptation because external flows are all about the shear of the flow. Okay, the rest of these settings are actually the defaults. Now, unfortunately, it only supports when you're using volume mesh. So when I did the sails as a surface part, I wasn't able to use it. I hope you'll be able to in your analysis. So let's go on to the settings. What settings are going to help us solve the most accurately? For anything external flow, I'm going to recommend an advanced level turbulence setup. This is exactly the same information that Royce presented when he was talking about your turbulence models. Excuse me. So that advanced level turbulence setup, it's using the kappa omega SST turbulence model. This requires a little bit of a change to our mesh settings. When you go into the enhancement layers, you want to make sure blending checkbox is checked. For layers, you're going to range from 10 to 15, 10 being a great starting point. The factor is going to be at 0.6 to 1.0. Again, the bolded numbers here are the recommended at 0.6. And you're going to set gradation to 1.25 to 1.5. When you're looking at the solver, you want to make sure you change to a tight convergence. You have lots of areas in your model or your domain that aren't going to be changing very much, and it's harder to detect when to automatically stop. With the tighter convergence, you'll be sure to have a good solution. And for that turbulence model, the kappa omega SST, we really recommend that you switch to ADV5. So, just kind of as maybe a pilot joke, if you will, this picture is of a plane experiencing the wake turbulence. Just another emphasis that the wake is really important on these external flow analyses. And what's kind of interesting, when I showed this picture to somebody else, they were like, oh, that plane's really causing a wake. No, the plane in front of that plane is really causing the wake, and this plane is actually about to experience that turbulence. So it's kind of to really emphasize that the wake is a little bit important. We are using an advanced turbulence setup to make sure we capture that accurately. Last, as far as settings, I'm going to ask everybody to think about the environment. Always a good thing to do these days, right? But what I'm talking about is we're actually trying to model a piece of the environment for these external flow models. So if we think about this picture I achieved from the web, there's boundary layers that are built. The trees can block the flow. A cityscape, if you're modeling a skyscraper in the middle of a city, the airflow down at the bottom at the city is going to be totally different than the airflow probably at the top of your skyscraper. The same is true for the sailboat. The wind at the surface of the water is significantly less than at the top of the mast. That's where you get your fractional rigs from, some of the sail design, all try to capitalize on what the expected velocity profile is for the sailboat from the change of the water, from the height of the water, excuse me. All right, so we have this spatial variation boundary condition. Can be done for the velocity, for the pressure, the temperature. Basically point it in a direction and then give it a profile curve to say the velocity is lower here, higher here, or whatever gradient that exists for your model. All right, so what did we learn today? We learned about prior proper preparation. There's all kinds of little sayings about that, but it's basically think about what you're trying to solve. Isolate what aspect you want to try to improve your design on and make sure everything leads towards that. In this case, we were working on the sails, so we wanted to do a flow analysis with air. If we were working with the hull, we might have used water instead. We want to think about the mesh. Mesh is everything for these analyses. We have a lot of tools to make it very easy, but when they don't fit for your model, or when you need something a little extra, I tried to give you some out-of-the-box techniques, some other options as far as how to get the auto-sizing to give you the mesh you want. And then last, we need to be environmental. We need to think about the environment. There's always turbulence. We need to think about that wake and make sure our model is sufficient to cover that, and also think about that spatially varying boundary condition that we can leverage to use it. All right, so we're going to go into a little bit of visualization. So this was thanks to John Wild, one of our support specialists. He made a very pretty picture of my model for me with beautiful particle traces. And I will try to switch to CFD at this point. So here's my boat model. I've colored the sails white and the hull red just to kind of help everything highlight. And I've put some particle traces on to allow us to see what possibly is going on as far as the interaction between these two sails. All right. Right now they're colored by the velocity, and you can see as the vectors that are the particle traces that are on the front side, the upwind side of the sail, actually slow down as they hit the mainsail. But what's happening with, why do we even have a jib on top of this sailboat? I'm going to try and look down on this model a little bit. And as I scroll back in, you can see the jib is being like this giant scoop accelerator for the particles going on the back side of the main. So we have slower particles on this side, faster particle traces on this side. The flow is accelerating on the back side of the main. Let's see what that does when we think about pressure. So this is now our particle traces colored by pressure. Lo and behold, when the velocity is slow, the pressure is high. When the velocity is high, the pressure is low. Simple Bernoulli's, right? But this is what makes a sailboat go. We're deflecting the wind to make a pressure gradient against those sails so that we can transmit a force or energy into the boat hull to make it go fast. All right, let's see what that looks like as far as model's not cooperating with me on my screen. There we go. We can look at isosurfaces. Now, I have these on. This is the little faint outlines you're seeing. I'm going to make them so isosurface, edit, and change them to shaded mode. All right, right now we're looking at positive pressure. Where do we get the positive pressure on the sails? Well, the jib, being that big scoop, is getting positive pressure because it's forcing the wind to change direction. We're also seeing positive pressure on the main. If we can maximize this area of positive pressure on this side of the mainsail, we can get more force or more energy out of the wind. Let's go ahead and turn the boat to the opposite side, the downwind view, and I'll change this to the negative pressure. Notice that behind these sails, we have areas of lower pressure, and that's setting up the pressure gradient, again, to make the sailboat go faster. And then for any of you who have been sailing, it also is what makes the boat tip over. But that's the fun and the excitement of sailing. So the idea, again, of these sail makers is how to get these sails to interact with each other to maximize getting lower pressure here without getting that pressure so low that the sail actually stalls. You can apply these same techniques to an airplane. When you get the pressure so low that the plane actually stalls, your airplane's not going to stay in the air very long. Not a good day for flying. So with that, I'd like to open it up if anybody has any kinds of questions.
So one question I had, Peggy, was, since you've worked with these, boat designers before, what do they really do in terms of analyses? And are they doing 2D cross-section runs of how the sails interact up the length of the mast? Or are they doing full 3D analyses? Where's the industry at that you've seen at least?
Okay, 20 years ago, right, it was all two-dimensional. We didn't have the computational resources. We didn't have the solvers capable of doing much more beyond 2D to the level of detail that they need to actually design sails. And a lot of 20 years ago, the sail making industry was like, nah, it's better to handcraft this as an artisan. Yeah, simulation builds slow sails. And that's totally changed. We're now seeing the full three-dimensional relieving effects that go on with these sails, and you can't capture that with just a simple 2D. 2D will get you started to let you know, hey, here's a basic shape, maybe as you're doing cross-sections going up the sail, you know, cross-section here as opposed to one here. But don't forget, we're talking about that environment where the velocity down here is very different than the wind velocity up at the top of the mast. Also, something you might have noticed when I turn the sail here, this sail has an awful lot of twist. The top of the sail has a very different angle to the wind than near the bottom of the sail. This happens to be a fractional rig, so the jib's only coming up so far. So how the main, excuse me, trying to move my model here, how the main up in this part is reacting to the flow is totally different than when you have maybe the belly of the sail. And if you'll notice, while I'm rolling the model around, the particle traces that were on the front side of the main actually lift up in the wake a little bit. It's the particle traces that went behind the main that are tending to stay more straight or more level. And that also has a profound effect. That's what I would call the 3D relieving effect as you're trying to do these analyses of the sails. So sailmakers spend an enormous amount of money trying to determine what is the optimal shape. And they are splitting hairs as far as, can the boat sail at 25 degrees or is it 25.5 degrees relative to the wind to give me that Remember, we're talking, you know, to add the acceleration of racing. It's all about how fast you can go. Well, think about car racing. It's the same thing. The level of detail is just amazing of what we're learning by using simulations. Is there anything else I could help anybody
Hi,
with?
Peggy. Yeah, just one thing I think that I can see right now. We had a message asking if you could discuss the hardware that you used to run this type of study.
This study, I think I used the laptop I'm presenting on right now.
Yes,
I actually did not send this job off to the cloud, although I think if I had pre-planned a series of test cases, I probably could have leveraged the cloud quite nicely. Get one set up, figure out, hey, this looks pretty much what I want, and then to do a sweep of angles, you know, wind angles, to complete and have a really nice profile of how this boat's going to sail relative to the wind with the sails at this trim. So my laptop is, I don't know, it's an HP EliteBook. So it's not really substantial hardware. This was able to run quite nicely.
I thought that might be the case, thanks. We just had another question as well, asking about if you could kind of explain the type of setup that you used, what boundary conditions you used, and if maybe you used a gradient for the wind, and if not, how would you do that?
I did use a gradient. Let's see what I can do here. All right, so we're going to go back into setup mode. Scroll my box out a little bit. And you can see I did use, these are the boat parts. And these two surfaces that I just set aluminum because I'm not doing any heat transfer through this. So it didn't matter what this solid was. But I selected these both as surface parts for the sails. Okay, on to boundary conditions. Let's see if we can see. The ground plane I left alone. It'll help mimic the fact that the water-air is a friction event and that the air is not going to move as fast across the water. I applied slip on the outer walls of what basically becomes my wind tunnel. And for the back is just a straight pressure. And unfortunately my widget is affecting, there we go, how I can rotate my model. And for this boundary condition, this is the velocity boundary condition. I'm going to go ahead and select it. I don't know if you can see over on the side, it says linear variation. We select it and edit it, you should see what I was able to select. You can see this blue arrows pointing in the upward direction. So down at the surface of the water, I wanted to specify one value for the velocity, and as I climbed up, I wanted to specify different velocities. So I used it as a piecewise linear, and this is in my direction, and I think if I edit this table, you can see I did add a profile, and we can plot it. So we have the velocity actually increasing from 10 knots to 16 knots over the length of the mast, or actually of my external box. Okay?
Yeah, I think that covers it, Peggy.
So we always got to go back to results. The results are always so much prettier.
No,
One of the
yeah,
things
no.
I did was I had fun with the textures to make the hull this kind of shiny red color. Anyway.
Yeah, so Peggy, I know you didn't really run this model for, like benchmark level meshing, but maybe showing what the mesh actually looked like, because it did capture, what you were expecting, at least in terms of the sail dynamics. There were some people asking how many elements, even with the light mesh that you did use, how long did it take to run? So I don't know if you just want to pull up maybe the status.
Yeah. Thinking about how best to show that. So the status file, right about here. So elements is what we usually, 2.2 million elements. Which, if I needed to get to the accuracy, perhaps for America's Cup, I probably would have doubled that. All right? And it just kind of an in general doubling of what I did to get the kind of resolution I wanted. Keep in mind, too, had I actually meshed the sails as volumes or actually suppressed the sails as volumes, I would have been able to use the mesh adaptation. So somebody that's maybe doing a car and the flow over a car, you would leverage the mesh adaptation, in which case you would start off with a mesh even less intense than this and let it do its thing, where it's adding the elements exactly where it needs them instead of wasting elements where you don't need them. Okay. As far as runtimes, this was one of those I, set it up, played with it a little bit throughout the day, and because I had my other aspects that I was supposed to be working on, I set it up to go when I left at the end of the day. I think it took maybe 2-3 hours after that. Came in the next morning, I have beautiful results, and there was able to create the presentation. Obviously, if that mesh increases or you're leveraging the mesh adaptation, that'll increase your runtimes a little bit. Again, if you throw more computational power at it, say using the cloud, leveraging that, you would be able to get better performance. Again, I was on a little laptop, not anything too high powered. I think along with that, I think we wanted to see what the mesh looked like itself, correct? So let's see if I can change my view to shaded mesh. So it's the mesh on the sails themselves. One of the things I might have looked at is if I wasn't getting enough resolution, maybe in this area of the sails, I could change that surface gradient, growth factor, a little bit lower still. 1.2, I changed it to 1.1. Maybe I'd go to 1.05 to have a little bit more fineness in the larger sections of the sails. But truly, there's not a lot that is changing with the wind or the airflow at that point. Most of it actually is happening right at the luff or at the leach of the sail. So I'm not sure that actually would have given me any better accuracy. But it just might have been something to try while I'm trying to say, yes, I really want to benchmark this to the best accuracy I can have. Now, if you were going to try and actually separate flow in this area, now you're going to need a finer mesh, but to separate flow, you're going to have geometry that would have stimulated that. So your geometry would have driven your mesh there. I hope that answers everybody's question.
Yeah, that pretty much answered that question. Here's one from one person who joined. Is there a particular reason why the domains are always rectangular? Now, he likes to use a domain which is more spherical in shape, so you can run a series of angles without a rematch. So he'll probably use...
Uh-oh. Now I hear a very loud hiss, like somebody's steam kettle. Not sure the audio is still going here, but I think I understood the question. Spherical can work, except you've got to figure out how you're going to transition from your inlet condition, which is going to possibly be a specified velocity, to that pressure condition to let the flow actually proceed out of the domain. One of the issues is if you have a sphere, and you have two hemispherical, I guess they're actually quarter spherical surfaces, you're going to have a line demarcating between them, and that line demarcating it, you're going to have both a velocity and a pressure condition applied, and that can cause issues because it's not physically real. If you can think to separate that, that works. I prefer to keep the model oriented in the global XYZ and then rotate my box, which is an externally created volume, and just rotate the box with the tools in geometry. I'm not sure it's going to allow me to do this. Go back to setup. Yeah, I really don't want to take off my
I would go under there.
at that point. Okay, but we do have the external volume creation, and that's what I used. I used CFD as external volume. I can specify exactly, wow, my boat's this long, I want my box this much longer, and use the 2/3 piece for the length, two lengths upstream, 3 lengths downstream, create my box, and then I type in an angle. And I type in that angle, and then it's real easy for me to say, oh, instead of 25 degrees, I want 24 degrees. And you can really precisely do that. That allows also to apply the normal velocity, which is much easier than figuring out the components, X, Y, Z, sines, cosines, to have to manually put that in. Leaves your force, any kind of wall calculator forces, also relative to the object, not the box.
Hey, Peggy, any experience on what sort of lift and drag accuracy you could look for with a without too much effort kind of number, and then an effort of large proportion to get a good mesh on kind of a sailboat? Any gut feel on that?
I think who asked that has to come to the next session on the NAC Airfoil 0012.
Okay, leave it at that for that one.
Truly, I think that'll answer that question very nicely. Is that if you just slap any old thing on a simulation analysis, that was my emphasis with putting the pieces together, that you really need to think about what you're going to do to make sure you're asking the right question. With a little bit of intelligence, I think you can get fairly accurate. With applying all the best techniques and the best practices, it can be, within 5%.
Peggy, could you do a little bit more with the visualization, just to take a look maybe on a cut plane at the vectors, just to show if there's any kind of reverse flow or recirculation?
There better not be, otherwise the boat's not going very fast. All right, let's see what I do. All right, everybody okay if I trash the particle traces on the isosurface? Let's remove, and we'll go ahead. Oops. Oh, I was right there. I'm sorry. Okay. We'll also go back to a smooth style view. All right, in results, we're going to add a cut plane. Use I turned it the wrong way. It's hard to get oriented. Now we're below the sailboat. All right, there's my sails. And we want to see what the vectors look like on this. Probably, since we're talking vectors, we really want to think about the velocity. So we're going to go ahead and show velocity vectors. I really can't believe I just did that. We get to start over again. I'm sorry. Go a little bit slower, change it to velocity magnitude, select vector settings. And we're going to tighten up our spacing a little bit. We need to make them a little bit smaller so we can see maybe some of the details. Now one of the things we might start looking at is this might be a little bit of separation. This is where the flows may be starting to go around. And anybody that's a sailor that maybe has raised, this is the optimal place to put your telltales. You know, for small boat racing. Of course, with the America's Cup, it's too small to see a little piece of tuft of yarn that might be wrapping around the back of your sail. But if you start to see, say, your telltales wrapping around to the back of the sail, you know you've done something with your leech to make the sail too tight. You don't have the clean flow leaving from the sail, and you're inducing drag, or that's slowing you down. I think we have to see the mesh on this. We'll do my best to show shaded mesh. One of the things you'll notice is there's all the extra layers that I did as a result for the turbulence model. With the flag, we added extra elements around here so that we were actually able to capture that. Now, if I were, like I said, if I really needed to do a very accurate solution, I would have probably doubled the size of the mesh that I actually used, and you would have seen that in this area as well. So one other area that might be of interest is the interaction between the jib and the main, or actually, here's the mast. Is there something we could have done with the mast to actually eliminate some of this pocketing that's going on behind it? Now, there's been some studies where they actually are trying to turn the mast depending on which angle the boat is to the wind. An awful lot of mast studies are being done where, especially on smaller boats, they're trying to block the mast to pre-bend it to affect the shape of the sails. A bunch of sailors are nuts, right? To me, the ultimate engineering sport, you're harnessing nature's energy to put it to make you go fast and have, you know, this exhilarating sport. You know, fluid flow, dynamics, vibrations, structural. It's kind of fun. Clearly, I really love to sail, so I hope everybody else shares my passion there. I know that's not always true.
Okay.
Hey, Peggy, we've I had a question. Oh, sorry, you carry on.
No, go for it.
I was just going to mention what we're just discussing about the ISO surfaces, whether it's possible to show a very low velocity ISO surface with some vectors on it also.
Ah, okay. You're taxing my abilities here.
Apologies, I'm not making them up, I promise.
Okay, let's get back to
Yeah, so you just open that up, switch velocity. Yeah, and just switch it to like a 0.01 sort of value for the ISO surface.
All right, so here's our velocity. It's kind of interesting. Check out that wake, right? With just a little bit more. And then you want to see vectors on this.
Put out like 0.01 for the velocity, and then turn on vectors.
It made a chia pet.
Yeah, and then turn down the length scale a little bit. Oop, down, there you go. So now if we kind of take maybe a top-down view.
Unfortunately, the blue on the bottom.
And Mike, I'll actually be talking about a way to do a offset distance ISO surface next time as well. So basically what he's looking at is a near velocity ISO surface. And there actually is a way to do like an offset ISO surface, almost like if you remember a long time ago, we could do like an offset surface with a plane. But we'll talk about that in about a month. Okay. So here you can actually see some of the reverse flow with the ISO surfaces, but if you switch it to pressure, might be able to get a better idea of coloring and depth of field. Color by result.
Yeah.
There we go.
Oh, much prettier, right?
Yeah, much better now.
You can see here's the leach of the jib, and there's something funny going on there, something funny going on here. Now, to funny being, yeah, the flow's not perfect. Well, we have a sail blocking the flow. So you would expect some of this, and this is what sail designers would be trying to maybe minimize to enhance their performance.
Okay. Well, Peggy, it's about the top of the hour. I want to thank you for putting this together. I know it's not your day job to do presentations like this, so I know everybody appreciates it. And just to remember, there will be a survey that will pop up as soon as you leave the session, and I really would appreciate if everyone could fill that out, add any ideas, add what you might want in terms of external flow. The next one that I deliver will probably be the last external flow we'll do for a little while. We'll do other specific content moving forward. So add whatever you want to hear, and I'll try to address it next month. The PowerPoint will be available based on that link I provided, autodesk.box.com/CFD8, because this is our 8th CFD webinar. And one thing that some people did request is maybe having this model just to play around with. It is a kind of a fun model, so I'll talk to Peggy and see if she's okay with sharing it. If she is, then we'll upload it to that folder, and you can then download it and hack away at it as you see fit. Just remember, some of this actually was built to create some problems so Peggy can try to demonstrate some meshing difficulties that you talked about earlier. So keep that in mind. I wouldn't be surprised if you start from scratch with your meshing. You'll see those same issues that you would then have to work through on your own. But that's a great learning experience, so I encourage you to play around with it if she provides it. So again, I want to thank everybody for joining, and next week we'll have a MoFlow raise your simulation IQ session. And even if you don't use MoFlow, I encourage you to come and learn something new. Thanks everybody, and have a great week.
Thank you, everybody.